Let's look at some sample problems now. The question here is, how do we prove that a certain motion is actually simple harmonic? Well, we learned from an example of mass and spring system that the net force exerted on a mass attached to a spring is equal to negative k times x, x here being the displacement away from equilibrium, and k is the spring constant. Now, in a more general sense, we don't have to have a mass attached to a spring. For example, a pendulum has no spring in it, it's powered by gravity. But at any rate, if you can show that the net force equals a negative constant, which we call effective spring constant, k effective, times x, x here being the displacement away from equilibrium, then the motion will have to be simple harmonic. This x does not even have to be a linear displacement. For example, in the case of a pendulum, we know this actually is an angle theta. When theta equals 0, then the pendulum is in equilibrium, the net force is equal to 0. And this does not even have to be a force necessarily, it can even be a torque. So if we can show the net torque also equals a negative constant times the displacement away from equilibrium, then the motion has to be simple harmonic. And we'll look at examples of that. Conversely, if we can also show that the energy of the system equals the sum of the kinetic and potential term. Of course, we know the kinetic term always equals 1/2 mv squared, but the potential term, it depends on what kind of potential it is. For simple harmonic motion, the potential has to be equal to 1/2 times a constant times x squared. Okay, so it has to be a quadratic potential, such as the case of a spring. If we can show that, then this has to be simple harmonic because we know a spring mass system has exactly the same form, 1/2 mv squared plus 1/2 kx squared. The only difference is that here this m does not have to be the real mass, can be effective mass, and the spring constant doesn't have to be real spring, can be what's called effective spring constant. And v is not independent of x, is related to x by v equals dx dt. Now, we learned that if we can show either of these, then the motion, if we solve the Newton-second law equation, you will get a simple harmonic solution. And here is the period of the simple harmonic motion. It is not only simple harmonic, but we can also find the period or the angular frequency. Okay, let's look at an example how we do that. First of all, let's revisit the example of simple pendulum. We learned how to approach the simple pendulum problem from Newton's second law. That is, we find the force, net force, and we find the net force equals a negative constant times theta, and we go from there. Let us see how we can resolve this problem, this time from energy point of view. Now, what is the advantage of energy approach? We only have to write down the kinetic and potential energy term for that mass. And since we're dealing with scalar quantities, as you know, energy is a scalar, we don't have to worry about vectors. In other words, we don't have to worry about directions of a force or torque. We don't have to worry about positive or negative signs, that sort of thing. We don't have to worry about components, x component, y component, because these are just scalars. Okay, now we know the standard energy form for this mass here consists of two terms. One is if the speed of the mass is v, okay, it's moving down or up with the speed v, then it's got a kinetic energy term 1/2 mv squared. What about the gravitational potential energy? Well, that depends on where we choose the ground level or zero level of gravitational potential energy. And for convenience, let's say we choose this point, that's the lowest point of the mass, as a zero potential level, which means when the object goes all the way down to the bottom, the potential energy is defined to be 0. Then how much potential energy does it have when the string makes an angle theta with the vertical line? Well, that depends on how much higher this mass is compared with the reference point. You know from this diagram, you know it's higher by distance h. How much is h equal to? Well, this is the length of the string going from here to there, so this length from here to there is L. And look at this right angle triangle here. This is L, the length of the string. This angle is theta, so from here to there, we have L times cosine theta. So what is h equal to? That will be the total length, which is L, minus that part, which is L cosine theta. Okay, so h equals L minus L cosine theta. Meanwhile, the speed v We're talking about linear speed here because it's 1/2 mv squared, not 1/2 I omega squared. Linear speed is related to angular speed by v equals omega L, right? And omega is d theta over dt. That's how fast the angle theta changes. This omega is the angular speed of the bob going back and forth. Let us plug both of these in to the expression for the mechanical energy of the bob. We have 1/2 m, and then v is replaced by L d theta dt, so we have L squared and d theta dt squared, plus the potential energy term, that's mgl, 1 minus cosine theta. This first term looks just fine because basically it is some sort of constant times d theta dt squared. That looks just like the actual expression we wanted, 1/2 mv squared. V is dx over dt. But the second term looks disappointing at this point because it's 1 minus cosine theta. Now theta is a variable here. What kind of functional dependency do we want for theta if this thing is actually simple harmonic? Well, you have 1/2 kx squared. That's your target, right? Since x is replaced by theta, don't you want 1/2 some sort of constant and times theta squared? Okay, so this is 1 minus cosine theta is not quite theta squared. It's not a quadratic potential, which is required. So we have a problem. And how might one resolve this problem? Well, you learn that when we used the force approach, we didn't quite get simple harmonic motion until we made some sort of approximation. You recall that? Okay, let's put the slide back on. In this slide, you learned that we had a sine theta, which make this equation very, very hard to solve. It's not quite simple harmonic. How did we simplify it? We say, oh, theta is very small, very much less than 1 radian, and therefore we say sine theta is almost equal to theta itself. That was the approximation we used. Without that approximation, it is not a simple harmonic motion. Since we want simple harmonic motion for the pendulum again, the only thing different is that we're going to use a different approach, but the motion is still the same, simple harmonic. We need the same exact type of approximation, and that is we're going to assume that theta is again very small. When theta is very small, we learned from math that cosine theta is roughly equal to 1, right? But of course it's always a little bit less than 1 because it's a cosine theta, so it's 1 minus something. Theta squared over 2 factorial, which is just theta squared over 2. Now, this is the approximation that's necessary to prove it's a simple harmonic motion. If we plug this in, then magically we have a theta squared. That's exactly the quadratic potential we're looking for any simple harmonic oscillation. So we now have a simplified version of the mechanical energy of the bob. 1/2 constant times theta dot squared. Theta dot is d theta dt. Next term is 1/2 sometime constant and then theta squared. If we compare this with the standard energy expression for simple harmonic oscillator, which is 1/2 mv squared plus 1/2 kx squared, we learned that there exists a 1-to-1 correspondence between these two expressions. See, 1/2 is still 1/2, right? Instead of x, we now have theta. That's okay, it doesn't have to be x. And instead of v, which is dx dt, I have theta dot, which is d theta dt. That's perfect. What about m? M is replaced by ml squared. So that is our effective mass, ml squared. And k, there is no spring here, is replaced by another constant, mgl. That replaces k. So those are the analogies. Now we know that this equation will lead to a simple harmonic oscillator. That means if we repeat the same calculation, we'll find that this expression for the pendulum will also lead to a simple harmonic solution, simple harmonic motion. And here is the period of the simple harmonic motion. Instead of 2 pi times square root of m over k, I must replace m with effective mass, which is ml squared, and k with the effective spring constant, which is mgl. Okay, so here's what I have. I have 2 pi times effective mass, ml squared, over effective spring constant, mgl. You cross out the m, you cross the 1 power of l, and magically we get the same exact expression, 2 pi times the square root of l over g. So you see, we actually get the same exact result whether we use the energy approach or force approach. In some cases, the energy approach is superior to the force or torque approach because, after all, it gives you only have to deal with a scalar quantity, which is kinetic and potential energy. You don't have to deal with components, vectors, that sort of thing. I want you to be familiar with both methods, force, torque, and energy, so that when you have a real problem to solve, you can try both methods or pick up one that is easier or better for you.